Yes, good morning, students. This is Anil Kumar Bojja, Assistant Professor of Chemistry, Government City College, Nayapur, Hyderabad. We have been learning about infrared spectroscopy regarding to organic chemistry, organic molecules. So, in previous classes, we have discussed about uh, infrared region where it will be in electromagnetic radiation, what kind of radiation will come under infrared region, and we have also studied about instrumentation, how the instrument would be infrared spectrometer, and what are the sources that we will use in IR spectrometer. There are three types of sources that we have studied in previous classes: nearest globar filament, and incandescent light. These are the three sources that we will use as IR radiation sources in infrared spectrometer. So let us discuss about what are the applications of IR spectroscopy in organic chemistry, and the energy levels of harmonic oscillator, and what is a vibration. These all properties let us discuss in present class. Right. See, compared to, I have been saying about infrared spectroscopy that compared to UV visible spectroscopy, the number of bands appeared in the IR spectroscopy are more and they are narrower. The bandwidth will be less. It is because the only transition taking place between vibrational and rotational levels, the energy difference, the molecule is undergoing to vibrational and rotational changes. Therefore, the energy difference between rotational and vibrational levels in a molecule will be less according to classical theory, so that the gap width, the bandwidth, the gap present under the band will be narrower one. The bandwidth will be narrow compared to the bandwidth of a signal obtained in UV visible spectroscopy in a case of IR. So many more bands than UV visible spectroscopy, fluorescence or phosphorescence. So fluorescence is a property, even phosphorescence is also the property when electronically excited molecule, when it undergoes to a deactivation. One, if molecule absorbs the energy, it undergoes to some physical changes. If the energy is sufficient enough to the molecule to participate in ionization, so that the molecule will also undergoes to the ionization process, so we will get the ions. The radiation regarding to X-ray, gamma rays, they are high energy radiation, uh, that is high energy radiation, so that molecules undergoes to the ionization process. Whereas if a molecule absorbs the radiation in the range of ultraviolet and visible region, what happens? The loosely held electrons with the molecule, or for suppose to say lone pair electrons are there on the heteroatom in organic molecules, they will first undergoes to the activation from their ground state energy level to first or second, third, fourth. They will undergoes to the activation. The electrons undergoes to the activation from ground state electronic level to first exit state level, second exit state electronic level, third exit state electronic level, even sometimes nth exit state electronic level also, depending upon the amount of energy absorbed by the molecule in the ultraviolet visible region. Of course, that may be possible, but the once the molecule undergoes to the activation to higher exit state, more than first exit state, If a molecule undergoes to a excitation to second, third, fourth excited levels, immediately they will come down to their first excited state level. Therefrom, they will undergoes to the deactivation process. The molecule undergoes to the deactivation. Molecule is undergoing to deactivation process. Is it really it is undergoing to the deactivation? No. Whatever the electron of atom of a molecule that was undergone to the activation, that will participate in a deactivation, so that we will consider that the complete molecule will be participated in activation and deactivation. Okay, so whenever the activated molecule undergoes to the deactivation process, it releases the energy. Where from that energy is releasing? First, the molecule is taking some energy from the electromagnetic radiation to participate in activation. From that activated state, it will again undergoes to the deactivation, and it will come down to its as usual position. During that process, the molecule releases energy to the surroundings. The energy will be the released energy will be in two ways. Either it may releases energy uh, in the form of heat, or sometimes molecule may also releases its excess energy during its deactivation to the ground state in the form of light. Whenever the deactivation process happening by the molecule by releasing of its excess energy in the form of heat, that deactivation is called as thermal deactivation. Whenever the molecule undergoing to the deactivation by releasing its excess energy in the form of light is called as photochemical deactivation, or radiative deactivation. So these fluorescence and phosphorescence, these are the two physical processes takes place by the deactivation of molecule in a case of radiative deactivation. Fluorescence is the process where the electronically activated molecule participate in deactivation, where the deactivation of molecule takes place between same multiplicity containing electronic levels. The singlet multiplicity containing electronically excited state come down to its singlet ground state by releasing its excess energy in the form of radiation, in the form of light. That is called as fluorescence. Wherever the activated molecule or the activated electron to its same multiplicity containing system, it will undergoes to the intersystem crossing process, ISC we will say. So the ground state singlet energy level, the molecule present at ground state singlet energy level S0 undergoes to a activation to the first singlet exit state or second singlet exit state. For suppose, therefrom it will undergoes to the intersystem crossing process by and that will deactivates to the triplet exit state, or it will transform from singlet exit state to triplet exit state. So that there from there from that triplet excited state to, if the molecule undergoes to a deactivation to singlet ground state energy level, during that deactivation process it will releases its excess energy in the form of radiation. That deactivation is called as, that process is called as phosphorescence. So fluorescence and phosphorescence. So IR spectroscopy will provide excess information regarding to UV visible spectroscopy. Uh, Even the information provided by the fluorescence and phosphorescence process uh, in a UV visible spectroscopy So we will get the more information than these processes also, right? Bands are also much sharper. It is because of only the transition taking place between vibrational levels and rotational levels, but not between electronic levels. Remember, guys, this is very important one. UV visible spectroscopy bands are you in a UV visible spectra, the bands are very broad, huge gap we will find between the bands, whereas in a IR spectroscopy, a narrow bandwidth we will find. It is exclusively because of the physical change that is happening in the molecule between rotational levels and vibrational levels, right? And pattern is distinct for given molecule. Yes, because of this process, because of this uh, peculiar quality, because of this important property, we could able to record the spectra of all. We could able to record the spectra for every molecule, and every molecule will get the different spectral pattern. Every molecule will contain its own spectral characteristics, its own bands in it actually. For suppose if there is optical isomers in the molecule. Optical isomers are the molecules contain the same molecular formula, but if they have difference in their optical rotation property. D glucose, L glucose, for suppose. D glucose in the sense it is the D is not the capital D. The D is a small d. Let me write here. See, this is capital D and this one is small d. So this capital D will provide the information regarding to the lost hydroxy group or hydroxy group at fifth position in carbohydrates, monosaccharides exclusively to say, whenever the hydroxy group present at the right side in monosaccharides at fifth carbon, that monosaccharide will be given as D configuration, D sugar, D monosaccharide. So even capital L will also be there. Capital L represents the molecule in which the hydroxy group will present at left side at last uh, chiral carbon atom, last chiral carbon atom in the monosaccharides. Simply to say, capital D will give the information regarding to the monosaccharide in which hydroxy group will present at right side at fifth carbon atom. Similarly, capital L, if we uh, uh, assign the monosaccharide, that that will give the information regarding to the presence of hydroxy group left side at the fifth carbon atom, at fifth carbon atom in the monosaccharides, glucose, fructose, mannose, glucose, iodose, stallose. These all are monosaccharides. Monosaccharides are the carbohydrates. They will not provide the simple sugar molecules, or the sugar molecules which are having lower molecular weight. So they won't undergoes to the hydrolysis process. For suppose if you take the disaccharide sucrose, if we take if we take as an example, sucrose will undergoes to the hydrolysis process and it will produce two monosaccharidic units, that are glucose and fructose, that already we have studied in a class of carbohydrates lesson in a final year. So here optical isomers, when we discuss about the optical isomers, there will be a matter of small d and small l. Small d represents dextro, whereas small l represents levo. Dextro in the sense the molecule rotates the plane polarization light, or the molecule rotates the plane polarized light towards the right side in a spectrometer, whereas levo if we have given, if a compound is a laboratory, means that molecule rotates the plane polarized light towards the left side. Why this rotation is happening like so means it is exclusively related with the spatial arrangement of groups, different groups or different atoms at chiral carbon. So optical isomers, they contain dextrorotation and levorotation. Means, for example, L-glucose, D-glucose, if we take L-glucose is a molecule where it will rotate the plane polarized light towards the left side. It will contain the optical rotation or optical activity value in negative scales, whereas dextrorotatory D-glucose, if we take, the D-glucose will contain the optical activity value in positive signs. So these are optical isomers. So optical isomers, they exhibit the similar spectral pattern in a IR spectroscopy. Of course, even fingerprint region, we may find some differences regarding to this optical isomers also in fingerprint region of IR spectroscopy. Right. So no other molecule will contain the same spectral pattern in IR spectroscopy other than if the molecules are optical isomers. Right. Next, good qualitative tool in the sense the based on absorption wave number value of the molecule or absorption maxima of the molecule in a IR spectra, we can easily identify the nature of functional group. So that is why that's why the IR spectrometer or IR spectroscopy is good qualitative tool. Right. Can be used for compound identification. Yes, it is exclusively important. Whenever the organic chemist synthesize his new molecule, he will go for IR spectroscopy. He will give that molecule pure sample to record the IR spectra of that molecule to identify the what kind of functional groups are there in that molecule. Are they definitely a chemist will perform the synthesis new molecule, he will plan for the new molecule by knowing the synthetic route, and he will contain a inherent idea that for what molecule is doing the research or for what molecule is planned the synthesis, so that basically he will contain some idea regarding to the presence of functional groups in final molecule, final product. So he will give the molecule pure sample to the IR spectra to cross check whether the functional groups are whether the functional groups are present or not in that hypothesized or uh, 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 assumed molecule, or whatever the functional groups, they have to be there in the molecule according to his assumptions. He will correlate whether the functional groups are not whether the functional groups are there in the molecule or not. So this is a good qualitative tool to identify the functional groups present in the molecule. Right. Also a quantitative tool in the sense it will provide the information quantitatively between uh, mm, uh, during the progress of chemical reaction. Of course we can identify how much completion of a chemical reaction can also be identified. Means simply to say a reaction progress can be administrated through IR spectroscopy. Right. Intensity of bands, not bond is a chemical bond. Band means it's a signal appeared or obtained in UV visible spectroscopy, IR spectroscopy. So it is a quantitative tool because the signal intensity or the band intensity is related with the amount of compound present in the uh, sample, present in the sample. So if we get more intense signals, more intense bands, that indicate the presence of that functional group will be more, means the quantity of the compound will be more with that exclusive functional group, right? Spectra usually shown as percentage of transmittance versus wave number. In a previous case in the sense UV visible spectroscopy, the spectra is drawn or the spectra is obtained with respective to the wavelength and absorbance. Absorbance will be taken on y-axis, wavelength will be taken on x-axis. But here, instead of absorbance, here the IR spectra utilizes the percentage of transmittance, whereas instead of wavelength, here we will take wave number on x-axis. So this is, of course, few points I have discussed. There are many applications by this infrared spectroscopy in organic chemistry. Not only in the organic chemistry, even in even in inorganic molecules case also we can study.